is acceptable to tap into the equipment grounding conductor (EG) from the main service entrance to provide an EGC for each of the 8 feeder circuits. This is commonly known as common grounding. According to the National Electrical Code (NEC), multiple circuits can be grounded via the same EGC as long as the EGC has a conductor's capacity sufficient to handle the combined ground fault current of all the circuits it serves. The subpanels will have to have another earth ground. Even though the feeder circuits have an EGC, the subpanels still require their own grounding electrode systems, such as a ground rod or buried pipe. This is because the EGC in the feeder only provides a path for ground fault current back to the main service panel, but it does not provide a local grounding connection for the subpanels. The NEC requires that all subpanels be grounded, and the most common way to do this is through a grounding electrode system that is separate from the main service entrance grounding electrode system. In electrical systems, grounding plays a critical role in ensuring safety and preventing electrical shock hazards. Grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and de-energize the circuit. There are 2 main types of grounding conductors: the equipment grounding conductor (EG) and the grounding electrode conductor. The EGC connects the non-current carrying metal parts of electrical equipment to the grounded conductor at the source, while the grounding electrode conductor connects the grounded conductor to a grounding electrode, such as a ground rod or metal water pipe. When dealing with multiple feeder circuits and subpanels, it is important to understand the specific grounding requirements outlined in the NEC. A feeder circuit is a circuit that originates at the service equipment and supplies one or more subpanels. A subpanel is a distribution panel that receives power from a feeder circuit and provides overcurrent protection for branch circuits. Firstly, it is acceptable to tap into the EGC from the main service entrance to provide an EGC for each of the feeder circuits. This practice, known as common grounding, is permitted by the NEC as long as the EGC is sized adequately to handle the combined ground fault current of all the circuits it serves. To determine the appropriate size of the EGC, refer to NEC Table 250.122. This table provides minimum EGC sizes based on the rating of the overcurrent protection device protecting the circuit. The EGC must be sized to carry the maximum ground fault current that could occur on any of the circuits it serves. Secondly, subpanels are required to have their own grounding electrode systems, even if the feeder circuits supplying them have an EGC. The EGC in the feeder circuit provides a path for ground fault current back to the main service panel, but it does not provide a local grounding connection for the subpanel. The NEC requires that all subpanels be grounded to a grounding electrode system that is separate from the main service entrance grounding electrode system. The most common method of grounding a subpanel is to install a grounding electrode system consisting of one or more ground rods or a buried metal water pipe. The grounding electrode must be connected to the subpanel's grounding bus by using a grounding electrode conductor. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. It is important to note that the neutral conductor in a subpanel should not be bonded to the ground bus bar. This is because the neutral conductor is already bonded to ground at the main service panel. Bonding the neutral conductor to ground at the subpanel would create a parallel path for neutral current, which could lead to objectionable neutral current flow and potentially create shock hazards. In summary, when dealing with multiple feeder circuits and subpanels, it is acceptable to tap into the EGC from the main service entrance to provide an EGC for each of the feeder circuits, provided that the EGC is sized adequately. However, subpanels are required to have their own grounding electrode systems that are separate from the main service entrance grounding electrode system. The neutral conductor in a subpanel should not be bonded to the ground bus bar. Grounding electrode systems. A grounding electrode system is a set of interconnected grounding electrodes designed to provide a low impedance path to earth for fault currents. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation. Permitted grounding electrodes include metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and ground rods or pipe electrodes. Metal underground water pipes must be in direct contact with the earth for at least 10 feet to qualify as a grounding electrode. The metal frame of a building or structure can be used as a grounding electrode if it is connected to the earth by at least one of the other types of grounding electrodes mentioned above. A concrete encased electrode, also known as a U for ground, consists of at least 20 feet of bare copper conductor encased in concrete. Ground rings are continuous copper conductors that encircle a building or structure and are buried directly in the earth. Ground rods or pipe electrodes must be at least 8 feet long and must be driven into the earth to a depth of at least 8 feet. The NEC requires that all grounding electrodes be bonded together to form a single grounding electrode system. This bonding is typically accomplished using a bonding jumper, which is a conductor that connects the various grounding electrodes together. The size of the bonding jumper is determined by NEC Table 250.66 based on the size of the service entrance conductors. Grounding electrode conductor. The grounding electrode conductor connects the grounded conductor at the service equipment to the grounding electrode system. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. The grounding electrode conductor must be installed in a manner that protects it from physical damage. If the grounding electrode conductor is exposed to physical damage, it must be installed in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, or cable armor. The grounding electrode conductor must be connected to the grounding electrode system using a listed connector or clamp. The connector or clamp must be suitable for the type of grounding electrode being used. Equipment grounding conductor. The equipment grounding conductor (EC) connects the non-current carrying metal parts of electrical equipment to the grounded conductor at the source. The EGC provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and de-energize the circuit. The NEC specifies the types of conductors that are permitted to be used as EGC. Permitted EGC include copper or aluminum conductors, rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit. The size of the EGC is determined by NEC Table 250.122 based on the rating of the overcurrent protection device protecting the circuit. The EGC must be installed in the same raceway or cable as the circuit conductors. If the circuit conductors are installed in separate raceways or cables, the EGC must be installed in each raceway or cable. The EGC must be connected to the metal parts of electrical equipment using a listed connector or clamp. The connector or clamp must be suitable for the type of equipment being grounded. Bonding. Bonding is the process of connecting together all non-current carrying metal parts of an electrical system to create a low impedance path for fault currents. Bonding is essential for ensuring electrical safety and preventing electrical shock hazards. The NEC specifies the requirements for bonding in various types of electrical systems. The NEC requires that all metal enclosures containing electrical conductors be bonded together. This includes metal enclosures for service equipment, panel boards, switchboards, and motor control centers. The NEC also requires that all metal parts of electrical equipment that are likely to become energized be bonded together. This includes metal parts of motors, transformers, and other electrical appliances. Bonding is typically accomplished using bonding jumpers, which are conductors that connect the various metal parts together. The size of the bonding jumpers is determined by NEC Table 250.102 based on the size of the circuit conductors. Ground fault circuit interrupters. Ground fault circuit interrupters, GFCIs, are devices that are designed to protect people from electrical shock hazards. A GFCI monitors the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the hot and neutral conductors, it indicates that current is leaking to ground. When a GFCI detects a ground fault, it quickly trips the circuit, interrupting the flow of electricity and preventing electrical shock. The NEC requires GFCIs to be installed in various locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. GFCIs are available in several different types, including receptacle-type GFCIs, circuit breaker-type GFCIs, and portable GFCIs. Receptacle-type GFCIs are installed in place of standard electrical receptacles. Circuit breaker-type GFCIs are installed in panel boards and provide protection for entire circuits. Portable GFCIs are used to protect portable electrical equipment. Surge protection. Surge protection devices, SPDs, are designed to protect electrical equipment from voltage surges, which are transient overvoltage events that can damage or destroy sensitive electronic equipment. Voltage surges can be caused by lightning strikes, power grid switching, or other electrical disturbances. SPD work by diverting the surge current to ground, protecting the equipment connected to the circuit. The NEC requires SPD to be installed in various types of electrical systems, including service entrances, panel boards, and branch circuits. SPD are available in several different types, including hardwired SPD and plug-in SPD. Hardwired SPD are permanently installed in the electrical system. Plug-in SPD are plugged into electrical receptacles and provide surge protection for equipment connected to the receptacle. Inspection and testing. Regular inspection and testing of electrical systems are essential for ensuring electrical safety and preventing electrical hazards. Inspections should be performed by qualified electrical inspectors who are familiar with the NEC and other applicable electrical codes. Inspections should include a visual examination of the electrical system to identify any potential hazards, such as damaged wiring, loose connections, or overloaded circuits. Testing should be performed using appropriate test equipment to verify the proper operation of electrical components and systems. Testing should include insulation resistance testing, ground impedance testing, and ground fault loop impedance testing. Any deficiencies identified during inspection or testing should be corrected promptly to ensure the safety of the electrical system. Arc fault circuit interrupters. Arc fault circuit interrupters, AFSIs, are devices that are designed to protect against electrical fires caused by arc faults. An arc fault is an unintentional electrical discharge that occurs when current flows through an unintended path, such as a damaged wire or a loose connection. Arc faults can generate high temperatures that can ignite flammable materials, leading to electrical fires. AFSIs work by monitoring the current flowing in a circuit and detecting the unique characteristics of arc faults. When an AFSI detects an arc fault, it quickly trips the circuit, interrupting the flow of electricity and preventing an electrical fire. The NEC requires AFSIs to be installed in various locations such as bedrooms, living rooms, and dining rooms. AFSIs are available in several different types, including branch circuit AFSIs and combination AFSIs. Branch circuit AFSIs provide protection for the entire branch circuit. Combination AFSIs provide protection against both arc faults and ground faults. Coordination. Coordination is the process of selecting and coordinating overcurrent protection devices to ensure that the device closest to a fault will trip first, minimizing the impact of the fault on the rest of the electrical system. Proper coordination is essential for ensuring electrical safety and preventing unnecessary power outages. The NEC requires that overcurrent protection devices be coordinated to provide selective tripping. Selective tripping means that only the overcurrent protection device closest to the fault should trip, while other overcurrent protection devices upstream from the fault should remain closed. Coordination studies are typically performed by qualified electrical engineers to determine the appropriate settings for overcurrent protection devices. Coordination studies take into account the characteristics of the electrical system, including the size and type of conductors, the transformer impedance, and the available fault current. Selective coordination. Selective coordination is a specific type of coordination that is required for certain types of electrical systems, such as emergency systems and critical operations power systems. Selective coordination requires that overcurrent protection devices be coordinated to ensure that only the device closest to a fault will trip, even under worst-case fault conditions. Selective coordination is more stringent than basic coordination and requires more detailed coordination studies. Selective coordination is typically achieved by using current-limiting fuses or circuit breakers with instantaneous trip functions. Current limiting fuses limit the amount of fault current that can flow through the circuit, allowing downstream overcurrent protection devices to trip before upstream devices. Circuit breakers with instantaneous trip functions trip very quickly in response to high fault currents, providing selective coordination. Grounding and bonding for sensitive electronic equipment. Sensitive electronic equipment, such as computers, servers, and medical equipment, is particularly susceptible to damage from voltage surges and other electrical disturbances. Proper grounding and bonding are essential for protecting sensitive electronic equipment from these disturbances. The NEC provides specific requirements for grounding and bonding sensitive electronic equipment. The NEC requires that sensitive electronic equipment be grounded to a dedicated grounding electrode system. The dedicated grounding electrode system should be separate from the main service entrance grounding electrode system. The NEC also requires that all metal parts of sensitive electronic equipment be bonded together using low impedance bonding conductors. The bonding conductor should be sized appropriately to carry the maximum fault current that could occur. Harmonics. Harmonics are unwanted currents or voltages that are superimposed on the fundamental frequency of the electrical system. Harmonics can be caused by nonlinear loads, such as electronic equipment, adjustable speed drives, and uninterruptible power supplies. Harmonics can cause various problems in electrical systems, including overheating of conductors and transformers, increased energy losses, and malfunction of sensitive electronic equipment. The NEC does not directly address harmonics, but it does require that electrical systems be designed and installed in a manner that minimizes the effects of harmonics. Harmonic filters can be used to reduce the levels of harmonics in electrical systems. Harmonic filters are passive or active devices that are designed to block or divert harmonic currents. Power quality. Power quality refers to the characteristics of the electrical power supply, including voltage stability, frequency stability, and harmonic distortion. Poor power quality can cause various problems in electrical systems, including equipment malfunction, reduced equipment life, and increased energy costs. The NEC does not directly address power quality, but it does require that electrical systems be designed and installed in a manner that provides adequate power quality. Power quality monitoring equipment can be used to measure and analyze power quality parameters. Power quality monitoring equipment can help identify and diagnose power quality problems. Voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to the conductor's impedance. Excessive voltage drop can cause various problems, including dimming of lights, reduced motor performance, and malfunction of electronic equipment. The NEC provides guidelines for minimizing voltage drop in electrical systems. The NEC recommends that voltage drop on feeder circuits should not exceed 3% and that voltage drop on branch circuits should not exceed 5%. Voltage drop can be minimized by using larger conductors, shortening circuit lengths, and reducing the load on the circuit. Conductor ampacity. Conductor ampacity is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables of conductor ampacities for various types of conductors and installation conditions. The ampacity of a conductor is affected by several factors, including the conductor's material, size, insulation type, and ambient temperature. The NEC requires that conductors be sized to carry the load current plus any applicable derating factors. Derating factors are used to reduce the ampacity of a conductor when it is installed in certain conditions, such as in a raceway with other conductors or in a high ambient temperature environment. Overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. The NEC requires that overcurrent protection devices be installed in all electrical circuits. Overcurrent protection devices must be sized to protect the conductors they serve. The NEC provides guidelines for selecting the appropriate size of overcurrent protection devices. Overcurrent protection devices must be selected to trip before the conductors they serve overheat and cause a fire. Short circuit current rating. The short circuit current rating, SCCR, of an electrical component or system is the maximum amount of short-circuit current that the component or system can withstand without being damaged. The NEC requires that electrical components and systems be rated for the available short-circuit current at the point of installation. The available short-circuit current is the maximum amount of short-circuit current that could flow at a given point in the electrical system. The available short-circuit current is determined by the characteristics of the electrical system, including the utility source, the transformer impedance, and the conductor impedance. Arc flash. Arc flash is a dangerous electrical explosion that can occur when a short circuit or other electrical fault occurs in the air. Arc flash events can generate extremely high temperatures, intense light, and high-pressure waves. Arc flash events can cause serious injuries, including burns, blindness, and even death. The NEC does not directly address arc flash, but OSHA regulations require employers to protect employees from arc flash hazards. Arc flash hazard assessments are performed to determine the potential arc flash hazards in an electrical system. Arc flash hazard assessments take into account the available short-circuit current, the clearing time of overcurrent protection devices, and the working distance from energized equipment. Arc flash protective equipment, such as arc-rated clothing and face shields, is used to protect workers from arc flash hazards. Working space. The NEC requires that adequate working space be provided around electrical equipment to allow for safe operation and maintenance. The working space must be clear of obstructions and must be of sufficient size to allow workers to perform their tasks safely. The depth of the working space is determined by the voltage of the equipment and the presence of exposed live parts. The width of the working space is determined by the size of the equipment. The height of the working space must be at least 6 feet 6 inches for the height of the equipment, whichever is greater. Enclosures. The NEC requires that electrical equipment be enclosed in enclosures to protect it from physical damage, moisture, and other environmental factors. Enclosures are classified according to their ability to protect against these factors. NEC enclosure types are commonly used to specify the level of protection provided by an enclosure. NEC Type 1 enclosures provide protection against contact with live parts. NEC Type 3R enclosures provide protection against rain and sleet. NEC Type 4 enclosures provide protection against splashing water and hose-directed water. NEC Type 4X enclosures provide protection against corrosive environments. Wiring methods. The NEC specifies the permitted wiring methods for various types of electrical installations. Permitted wiring methods include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, non-metallic conduit, cable trays, and various types of cables. The choice of wiring method depends on the specific application and the environmental conditions. Wiring methods must be installed in accordance with the NEC requirements. Raceways. Raceways are enclosed channels that are designed to hold and protect electrical conductors. Raceways include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, and non-metallic conduit. Raceways must be installed in accordance with the NEC requirements. Raceways must be supported properly and must be protected from physical damage. Cables. Cables are assemblies of 2 or more conductors that are insulated and enclosed in a protective sheath. Cables are available in various types, including non-metallic sheath cable, armored cable, and metal-clad cable. Cables must be installed in accordance with the NEC requirements. Cables must be supported properly and must be protected from physical damage. The information provided is intended for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work.